Let's talk about basic regularization of trees. In general, when we want to regularize a machine learning model, we want to control the complexity of that model. For example, for gradient-based methods like neural networks or even linear or logistic regression models, we impose some norm constraints on the weights. These type of measures are considered indirect approaches. When it comes to tree-based methods, we will use more direct approaches. For example, we want to control the total number of decision nodes. A decision tree, when we fit on our training data set, is going to maximally overfit on that. We can even see those regions where we fit just a single data point. And that's overfitting. We don't like that. In order to counteract this kind of behavior, we want to control the complexity of our trees. For example, we can put some limits on the number of leaf nodes that we can have or on the maximum depth of the tree. And during the tree building procedure, when we hit these limits, we will stop this process. And overall, we will have a simpler tree. This type of stopping early is called pre-pruning. And this works entirely on the training data. These parameters, such as number of leaves or the maximum depth, are called hyperparameters, and we need to use cross-validation to select the optimum parameters in this case. So we just saw pre-pruning. There is also another version of this, which we call post-pruning. In this case, we start with a complex tree, then we trim backwards. There are again a near infinite number of options for this one, but the simplest one is called reduced error pruning. In this one, we iterate over our leaf nodes, then we try to remove them. We look at the validation performance. If it doesn't hurt the validation performance, then we remove those leaf nodes, and overall we have a simpler tree by doing that. In the modern world, this post-pruning approach is not that popular. And even we see that the sklearn library doesn't implement it. For that reason, we won't use post-pruning in this class. Okay, we reached our hands-on section. In this section, we will use sklearn library, and we will apply pre-pruning by controlling the maximum depth, maximum number of leaf nodes, and the minimum impurity decrease parameters. And then we will see how we can fit our trees with these parameters. Let's open our notebook and start our exercise. Let's open our notebook. It's called DTEL1 prune. In this notebook, we will apply pre-pruning with the sklearn trees. We will try to control our trees by limiting the maximum depth, maximum number of leaf nodes, and minimum impurity decrease. Let's first create a dataset. Here I'm using some random functions, but I have this seed here so that when you run this notebook, you will get the same dataset as me. Here is my axis, then I create my y's using these. Let's see the plot of the dataset with this, and overall I have this dataset. Here y is a continuous variable. Because of that, we will have regressors. Let's start with the maximum depth. It's actually quite simple. I will import my decision tree regressor like this from the sklearn trees. And for my predictions, I will use these numbers between -2 and +2, then I will plot those. Let's define this function, plot depth. In this function, I will first get my decision tree with the max depth parameter. Then I will fit that on my dataset. I simply call this fit function, and it fits my tree on my dataset. To get my predictions, I simply call the predict function, and I call that on my prediction data points that I just created here. Then I will plot my results. Then I will run this for multiple maximum depth parameters. Let's look at our plots here. So if I increase this maximum depth, I expect to see more complex trees. Let's see if that's the case here. With the max depth of 1, I have this decision tree. So as you see, I have a single split point here. Before this split point, I return this value here, which is close to 0. After this split point, I return this value, which is something close to 4. With the maximum depth of 2, I have a more complex tree. As you see, I have more split points, this, this, and this. And similarly, before and after, I return these values. With the max depth of 3 and 4, things even get more and more complex. As you see, we have even more split points here. And as we go all the way to 6, this is the most complex one. Let's play with the maximum number of leaf nodes this time. I'm using the same tree just like before, but this time I'm just changing this parameter here, max leaf nodes, and I will pass my parameters there. And over here, again, when we think about it, when I increase the number of maximum leaf nodes, again, I should expect to see more complex trees, right? Makes sense. So let's have this for loop here and plot our results. With the max leaf of 5, I have this decision tree here. As you see, these are my split points. With the max leaf of 10, I see more complex tree. And overall, as I keep increasing it, things will get even more complicated. These ones, I even have more and more split points because my tree gets more complex. I have more depths as well. Let's talk about this last one called minimum impurity decrease. This is kind of different because with the first ones, once we increase those, we got more complex trees. With this one, we will see a reverse effect because in this one, the tree grows if a node induces a decrease of the impurity greater or equal to this value, greater than or equal to this value. So this means that if I increase this, actually, I won't allow the tree to grow that quickly. Over here, that node will turn to leaf node if it cannot induce a decrease of impurity greater than or equal to this value. Overall, that parameter is calculated like this, or that value. And as I said before, this will have that reverse effect. If I increase this, in this case, my tree cannot grow. That decision node will just become a leaf node if it cannot satisfy this. Let's see our results. I am running this with smaller numbers. I have the minimum impurity decrease of 0.01, 0.02, 0.03, 0.04, all the way to 0.06. As I said before, once we increase this is a threshold, I will have simpler trees this time. And overall, this is how we apply the pruning idea. And as you see, this is quite simple, and this is a good start to build your trees for your final project.